Good morning, students. So let us continue with the last class. So now let us discuss about PCON registers and power saving modes of 8051. So in the last class we were discussed regarding SCON, SBUF, and how the serial ports are getting transferred, how the baud rate is getting doubled. That and all we discussed. We are discussed with many examples also. So let us do the continuation of the things. So PCON registers. This is one of the important type of registers. Here in PCON registers, we have a SMOD. It is of 8 bits. It is bit 0, bit 6, bit 5, 4, 3, 2, 1 and 0. And each will be represented in such a way. This is a frame or bit registers of PCON, which will be of ideal, PD, G of 0, G of 0, G of 1, and this are not considered. So here the SMOD is a baud rate is twice as much higher by setting this bits, and GF1 is a general purpose bits. GF1 general purpose bits available for use. GF0 is general purpose bit available for the use, and PD is nothing but by setting this bit the microcontroller enters into the power down mode. Ideally, by setting this bit the microcontroller enters to the ideal mode. By setting this bit the microcontroller will enter to the ideal mode, and by setting this bit it will enter into the power down mode. So that means each bit is having significant operation by doing so. Generally speaking, the microcontroller is inactive for the most part and just waiting for some extra signal in order to take its role in show. This can cause some problems in case of batteries which are used with a power supply. In extreme cases, only the solution is to set the whole electrons in sleep mode in order to minimize the power consumption. So PCON registers in power consumption modes in 8051, which will plays a major role as I told. In extreme cases, only the solution is to set the whole electrons in the sleep mode in order to minimize the consumption of power. In ideal mode, upon an ideal bit, upon an ideal bit, the ideal bits of PCON register is set. The microcontroller turns off the CPU until while the peripheral units such as serial ports, timers, interrupt systems continue operating normally. In ideal mode, the states of all the registers and input-output ports remains unchanged. I'll repeat. In ideal mode, the ideal mode of PCON is set. That means it is set as 1. The microcontroller turns off the central processing unit, while the peripheral units such as serial ports, timers, interrupt systems continues operating normally. And in ideal mode, the state of all registers input-output ports remains unchanged. In order to exit the ideal mode and make the microcontroller operate normally, it is necessary to reset. It will cause the ideal bit to be automatically cleared and program resume the operation from instruction having set the ideal bits. Next, power down mode. By setting the PD bits, the PCON register from within the program, the microcontroller is set to power down mode. As we have shown in the previous slides, the PD is nothing but power down mode. By setting that, we can set the PCON register to power down mode. In power down mode, the internal oscillator is off and reduces the power consumption enormously. In this mode, internal oscillator is off and reduces the power consumption enormously. The only way to get the microcontroller back to normal mode is reset. The only way to get the microcontroller back to the normal state is making it to reset. While the microcontroller is in power down mode, the state of all special function registers and input-output ports remains unchanged. When the microcontroller is in power down mode, the state of all the special function registers and input-output ports remains unchanged. By setting it back into the normal mode, the contents of special function register is logged, but the contents of internal RAM is saved. By setting it back into the normal mode, the contents of special function register is lost, but the content of internal RAM is saved. So this is about SCON registers. So now let us discuss with the next topic today, that is a new one. So according to your syllabus, so we are at the stage of module number 4. Okay, so here I have planned a few more programs on serial ports on assembly as well as C, which I'm going to do it in next class. But as of now, I'll start with module number 5, that is 8051 interrupts. And in today's class, I'll start 8051 interrupts. Okay, so let us start the interrupts in 8051. Okay, so this is module number 5. So what is an interrupt? So we already discussed many a times in the basics, that is interrupt means interruption. So if some program is going, it is in run, and if you want to stop the program at the present condition, you will put an interrupt. Okay, so it's like an interruption. So in the introduction part, we have the single microcontroller can serve several devices by two ways, that is interrupt and polling. In interrupts, whenever any device needs its service, the device notifies the microcontroller by sending it an interrupt signal. Upon receiving an interrupt signal, the microcontroller interrupts whatever it is doing and serves the device. That's what the interrupt means. That means any of the interrupt signal is uh, provided in the microcontroller, it will give the priority to it and it will stop the present work and it serves the interrupt. In polling, the microcontroller continuously monitors the status of all the devices in round-robin manner. When the condition or for a given device are met, it performs the service. After that, it moves on the monitor the next device until everyone is serviced. Then what is an interrupt? An interrupt is an external or internal event that interrupts the microcontroller to inform it that the device needs its service. So kindly remember this important point. The interrupt is an external or internal event. It can be an external event or an internal event that interrupts the microcontroller to inform. That means here we can give in 8051 we can provide an interrupt with hardware as well as software. So the microcontroller is going to inform the device that needs its service. The program which is associated with the interrupt is called interrupt service routine. The program which is associated with interrupt is called as interrupt service routine, in short form ISR, or interrupt handler. Okay, next, the difference between polling and interrupts. So the first column is indicating about polling and the second column is indicating about interrupts. In polling, the microcontroller continuously monitors the status of all the devices in round-robin manner. When the conditions are for a given device is met, it performs the service. After that, it moves on to monitor to the next device until everyone is serviced. But it interrupts whenever any device needs its service. The device notifies the microcontroller by sending an interrupt signal. Upon receiving an interrupt signal, the microcontroller interrupts whatever it is doing and serves the device. This is the main difference between polling and interrupt. In polling, the method is not efficient since it will waste much of the microcontroller time by polling a device that do not need the service. But in interrupt service, only those devices which needs the service and hence it is efficient. That means from this point we can call that interrupt is more efficient than polling. It is not possible to assign the priority since it checks all the device in round robin fashion. But in interrupt, each device can get an attention of the microcontroller based on the assignment priority. Okay, that means you can assign the priorities. In polling, ignoring a device request is not possible. The micro can also ignore or mask a device request for service. Vectored or non-vectored interrupts. So these are the two types of interrupts. Where here let us discuss about vectored interrupts. The devices that are vectored interrupts are assigned an interrupt vector. This is a number that identifies a particular interrupt handler, that is nothing but interrupt service routine address of this interrupt is fixed and it is unknown to central processing unit. Next, when a device is interrupts, The central processing unit branches to the particular interrupt service routine. All the 8051 interrupts are vectored interrupts. All the 8051 interrupts are vectored interrupts. So non-vectored interrupt means it is an interrupt who has a common interrupt service routine which is common to all non-vectored interrupts in the system. The address of this common ISR is known to the central processing unit. However, the CPU crucially does not know which device causes the interrupt without polling each input-output interface in a loop. Once the interrupt occurs, once these are used typically on faulty condition for a system reset function. So non-maskable interrupts and maskable interrupts. So, maskable versus non-maskable interrupts. This is very important difference. It then ask in Viva point of view also. In maskable interrupt, a maskable interrupt is one that the programmer can ignore by setting or clearing a bit in an interrupt controls register. Typically, a microcontroller might allow a multiple interrupt source, but the application required only few of them, and the programmer can mask off the unused interrupts. But in non-maskable interrupts are those which do not get gated by the interrupt control register. But here you can setting or clear by the bit of interrupt control register, we can able to mask. But here it is not possible. They always interrupt no matter what state the microcontroller is in. Typically, these are used for critical or fatal condition of the system reset function. Okay. So next, interrupt service routine. The short form is ISR. For every interrupt, there must be interrupt service routine or interrupt handler. When an interrupt is invoked means called, the microcontroller runs the interrupt service routine. For every interrupt, there is a fixed location of memory that holds the address in interrupt service routine. The group of memory locations set aside to hold the address of interrupt service routine is called as interrupt vector table. Steps in executing an interrupt. Upon activation of an interrupt, the microcontroller goes on the following step. So there are three steps. Step number 1. It finishes the instruction it is executing and saves the address of the next instruction, that is PC, on the stack. It also saves the current status of all the interrupts internally that is not on the stack. It jumps to the fixed location in the memory called the interrupt vector table that holds the address of interrupt service routine. These are the three steps which will be used for executing an interrupt. Again, I'll repeat, it finishes the instruction. It executes and saves the address in the next instruction, that is PC, on the stack. It also saves the current status of all the instructions internally that is not on the stack. It jumps to the fixed location in the memory called interrupt vector table that also holds the address of interrupt service routine. Next, fourth step is microcontroller gets the address of interrupt service routine from the interrupt vector table and jumps to it. That means it starts executing the interrupt service routine until it reaches the last instruction of the subroutine, which is return interrupt, that is RETI, return from the interrupt. Upon executing the RETI instruction, the microcontroller will return to the place where it was interrupted. That means the program will be getting executed. When you provide an instruction RETI, it will stop the execution of the program. It will perform the interrupt operation. When it receives RETI execution, first it gives the program counter address from the stack by popping the top of 2 bytes of stack into the program counter. Then it starts to execute from the address. Interrupt in 8051. There are 6 interrupts in 8051. Set, that is power up reset, power up reset. 2 interrupts are set aside for timers. One for timer 0, one for timer 1. 2 interrupts are set aside for hardware external interrupts, that is P3 to P3.3 for external hardware interrupts, INTO and INT1 for external one or XMAC 2. The serial communication has a single interrupt that belongs to both receive and transfer. So in serial communication, we have a single interrupt for both receive and transmission. So interrupt vector table of 8051. This is the interrupt vector table, how it's going to look. So these are the interrupts and these are the source and this is the vector address. So the system reset is represented as source as RST and the vector address is 0000H, external 0, IE 0, 0003H, timer 0, TF 0, that is 000BH, external 1, IE 1, 0013H, timer 1, TF 1, 001BH, serial port that is RI or TI that is 0023H. These are the vector address. How we can able to enable or disable the interrupts. Upon reset, all the interrupts are disabled, that is nothing but masked, meaning that none will be responded to by the microcontroller even if they are activated. Upon reset, all the interrupts are disabled or masked, meaning that none will be responded to by the microcontroller even if they are activated. The interrupts must be enabled by the software in order for a microcontroller to respond them. Okay, that means if you want an interrupt to be responded to the microcontroller by a software, you need to enable it. There is a register called IE, that is interrupt enable, that is responsible for enabling, that is unmasking the interrupts, and disabling, that is masking the interrupts. So for masking or unmasking the interrupts, we will make use of interrupt enable register, that is IE register, which is very important for enabling the interrupt or disabling the interrupt, masking the interrupt or unmasking the interrupt. So IE register, that is interrupt enable register. So IE register, the interrupt enable register is having an 8 pins, that is TH0, ET0, EX1, ET1, ES, X, X and E of A. These two pins we are not going to use. EX0, that is enable or disable the external interrupt 0. ET0, enable or disable the timer 0 overflow interrupt. Enable or disable the interrupt timer 1. This one again timer 1 overflow interrupt. ES, that is enable or disable the serial port interrupt. EA means enable or disable all the interrupts. So bit 7 of IE register must be set to high to allow the reset of the register to take effect. The value of EA. If EA is equal to 1, the interrupts are enabled and will be responded to if their responding bits in IE are high. If EA is equal to 0, no interrupt will be responded to, and even if the associated bit in IE register will be high. Again I'll repeat, if E of A, that is all interrupts, it is 1, the interrupts are enabled. If it is 0, no interrupts is responded, that means it will be disabled. And it will be responsible for if their corresponding bits in IE are high. Here, even if associated with IE register is high. Next is actually timer interrupts. So I don't want to go further topics because let you brush up with this topics first thoroughly. So about 8051 interrupts and all. Today what and all we discussed? We discussed about PCON registers. So detailed of 8051 interrupts, this introduction and what is an interrupt we discussed. As I told, it is external and the internal events and differences between polling and interrupts we discussed, and what is vectored and non-vectored interrupts. This is also important question for Viva. Go through properly. Maskable and non-maskable interrupts. So interrupt service routine, that is ISR, and what are the steps we are taking to execute an interrupt. It is very important. And the vector table in 8051, and how we can able to enable or disable the interrupts. And finally, interrupt enable register structure. So this we have discussed. So I hope you understood the session. So if anything is there, let's discuss. And We'll catch for the next session. I'll stop at this point. Okay.